Okay, guys, so we need to work some homework here. And I think that what I'm going to do, because the chapter 11 is probably a little bit easier than the chapter 17. And I do want to do these as two separate recordings. I think maybe we'll do the chapter 17 here first, and then I'll come back and do the chapter 11 afterwards. So let's start with the chapter 17 material. Since that's going to require just a little bit more work, and again, I'll remind you to click both of these to get your point for doing those. But then let's go over here to question 1. Okay, so state police believe that 20% of the drivers traveling on a major interstate highway exceed the speed limit. They plan to set up a radar trap and check the speeds of the first 50 cars which pass the trap. Answering the following. So using the 68, 95, 99.7 rule, we want to draw and label the distribution of the proportion of these cars the police will likely observe speeding. Well, if we believe that 20% of the drivers exceed the speed limit, then our distribution should be centered at 0.2. So we're looking either here or here, okay? That's not, these are both centered at 0.8, so we can rule out A and D as possibilities. Now, the other thing that we want to do here is look at what our standard deviation should be. So if you go back to the formula that we did for the standard deviation for proportions, and by the way, this was given in the slides for chapter 17, it should be, and I can bring those up for you, but you should have seen the formula there that the standard deviation we were looking at was the P times the Q over N. And the P we defined there, and the Q was the 1 minus P. That's what we were working with. So for this particular problem, our P is the 0.2 from the 20%. So we would be looking at the square root of 0.2 times 1 minus 0.2 would be 0.8 over the number of cars, the N would be the 50. Okay, so if we pull up our calculator and I do the square root of 0.2 times 0.8 and then divide that result by 50, we're going to get about 0.05, about 0.06 from that. So looking at this, notice, let me clear those drawings. 1 standard deviation is here, 2 here, 3 here. Well, I'm adding about 0.06 to it. So 0.26 would be 1 standard deviation, 0.32, and then 0.38. That actually seems fairly reasonable given that blocking. Let's just check the other to make sure. Well, 0.26 would be then 0.32, then 0.38. That's awfully far away from 0.04. So that's not likely to be correct. So we would want to choose B to have the correct spread. Do you think the appropriate conditions necessary for your analysis are met? Are the conditions necessary to use a normal model met? All right, well, let's look at it. In order to use a normal model to measure to model these proportions, we need to make sure that we have randomization. So looking at this, we're setting up a radar trap to check the speeds of the first 50 cars that pass the trap. Well, in a way, that's not totally random because I'm probably setting up that road trap on a specific location. So let's say that I were to set my road trap on, you know, I-4, that's probably different than what I would get if I set it up on, I don't know, Aloma Avenue, right? I'd probably have two different readings for those two values. But if we assume that this estimate is representative of the place that they're setting up the trap, then that would be representative, whatever would fly by them, right? Now, if I'm setting up a speed trap, again, the time of day might matter. So the speeds of the first 50 cars that pass the trap might not match, you know, if we're talking about rush hour versus non-rush hour or something like that, right? So again, it's not completely random. What else do we need to check? We need to check that we are going to have at least 10 successes and at least 10 failures. Well, 20% of the 50 cars, we would do 0.2. Well, here we go. 0.2 times 50. And 0.2 times 50 is 10. 10 is at least 10, so we're okay there. And then 1 minus 0.2 is 0.8 times 50. That would be the remaining 40. Both of these are bigger than 10, bigger than or equal to 10. So we're okay with meeting that condition. And then our 50 needs to be less than 10% of the total population of cars. I feel relatively confident that that 50 would be less than 10% of all cars that are going to go by our speed, you know, travel that roadway. So all of those conditions are met. The only thing that we would worry about here is the randomization. So our success failure condition is met, the 10% condition is met, but I would say the randomization is not met, although the sample might be representative of the cars on that road. So if it, you know, we can proceed with it, but that randomization condition is a problem. All right. It is believed that nearsightedness affects about 10% of all children. A kindergarten has registered 161 incoming children. Complete parts A through C. Okay. Can the central limit theorem be applied to describe the sampling distribution for the sample proportion of children who are nearsighted? All right, we have 161 incoming children. That's not going to be random, so we're not missing that condition. I mean, we're not meeting that condition. I would expect 10%. So 10% of 161 is 16, and then 1 minus 10% would be the remainder, so 145-ish. Both of those are bigger than 10, so I'm relatively comfortable with the idea that our success failure condition is met. Now 10%, 161 is less than 10% of all children. Yeah, that's fine. So I'm satisfied with everything except that randomization condition. So let's see what we have. Our choices for no is the randomization and success failure conditions are met, but the 10% is not. The randomization and 10% are met, but the success failure is not. So we would have to assume that these children are typical of the population to satisfy the randomization condition. So that's okay. So our 10% success are met. So we would say yes here, because the only condition that's missing is that randomization condition. And again, if we assume that these are representative of the population, then we can assume that that condition's met. Check this, sketch the sampling model. Now, again, if it's centered at 10%, I want 0.1 in the middle. So I can rule out these last two because both of these two are centered at 0.1. So now we do the same thing to find the standard deviation that we did before. We say our standard deviation would be 0.1 times 1 minus 0.1, so 0.9, over the number of children, 161. Let's plug that into our calculator. So I'd go square root of 0.1 times 0.9 and divide that by 161. And we get 0.0236-ish. All right, so from 0.1, my one standard deviation out would add 0.02 to that. All right, so let's add 3 standard deviations. So I want to go 0.1 plus 0.0236. Once, twice, 3 times will take me to about 1708. So about 1708 would be closer to this one than to this one for 3 standard deviations. Let's subtract it. 0.1 minus 0.0236 3 times to get the 3rd standard deviation out would be about 0.02. 0.02 is closer to this than it is to this. So I'm going to choose option A here. How many of the incoming students might the school expect to be nearsighted? Well, I would expect somewhere between these values. So notice 2 standard deviations out. So I'm going to go 0.1 minus 0.0236 gives me, whoops, times 2 for 2 standard deviations below. And why am I doing 2 standard deviations below? Because remember, from our 68, 95, 99.7 rule, 2 standard deviations will capture 95% of the data. So this percentage would be the 2 standard deviations below. So that percentage of my 161 children, so I go times 161, would give me a lower estimate of somewhere around 8.5 children. And 2 standard deviations up times the 161 children would give me about 23.6. So between 8 and 24 children would be 95% of my data. So that's what we might expect. Oh, they want us to use 3 standard deviations to get almost all of them. So notice the only one it could possibly be, I don't need to recalculate, has to be B, because it's got to be lower than 8 and more than 24, because I'm going 1 additional standard deviation. Based on past experience, a bank believes that 7% of the people who receive loans will not make payments on time. The bank has recently approved 300 loans. What are the mean and standard deviation of the proportion of clients in this group who may not make timely payments? Well, our mean would be that 0.07, where we believe the value is, so 0.07. And now to get the standard deviation, we're using that exact same formula. We're going to say that this is the square root of 0.07 times 1 minus 0.07, which is 0.93, over the number of loans, which is 300. So let's pull out our calculator. .07 times 0.93 and divide by 300. We get 0.0147. So 3 decimal places, we'll round that to 0.015. What assumptions underlie our model? All right, so the randomization idea, well, this probably is not going to be random, but we would assume that these loans are typical of the loans that the bank receives, and that would satisfy our randomization condition, right? The success failure, 0.07 of 300 would be about 21, and that's bigger than 10. And 93% of 300 would be the remainder, so about 279, and that's bigger than 10, so our success failure condition is met. And then the 10% condition, 300 is probably less than 10% of all of the loans that the bank issues, so that's met. So everything is met except the randomization, right? But again, if we assume that the bank is, that these loans are typical of all of the bank loans, then that would satisfy that randomization condition. But we're going to go ahead and choose the randomization condition is not met. And we are good if we assume that they are typical of the loans. So with reasonable assumptions about the sample, all conditions are met. So we just need to assume that these 300 loans are typical of all bank loans that the bank makes. What is the probability that over 8% of these clients will not make timely payments? Okay, so my mean 5. So that's one standard deviation up. So 0.08 would be right about there. 8% of these clients will not make timely payments would be everything over here. So I want that area under the curve. So now to get that area under the curve, remember we're using the normal CDF key. So I'm going to go over to my calculator. I'm going to do second distribution, normal CDF. My lower bound is the 0.08. Upper bound, I'll just go out to infinity, so I'll put in a bunch of 9s. The mean is 0.07. And that standard deviation is 0.015. And we get about 25.2, right? So 0.252. A company compiles data on a variety of issues in education. In 2001, the company reported that the national college freshman to sophomore retention rate was 76%. Consider colleges with freshman classes of 600 students. You want to use the 68, 95, 99.7 rule to describe the sampling distribution model. All right, so our retention rate was 76%, so that's where we're going to center it at 76, which means I'm only looking at these two. And this is a class of 600 students. So when I do my formula for the standard deviation, we're going to go square root of 0.76 times 1 minus 0.76 would be 0.34, no, 0.24 over 600. The number, the n is the 600. All right, so let's pull out the calculator. 0.017-ish. All right, so if I add 3 of those to the 0.76 that's the mean, my upper standard deviation should be about 0.812. 812 would be, okay, they're both at that value. So let's look at one standard deviation up. So adding 0.017, my first standard deviation is going to be at whoops. .777-ish. All right, so this is a distance of 0.06. So each of these would be about 0.01. So my first standard deviation should be about 0.77. This is about 0.77 here. So that matches, as does this one. No, this is too far over. Because this would be 0.77, 0.78, 0.79, 0.8, 0.81. So that's a little too far. Oh, 0.81 here. That is our third standard deviation, just past 0.81. So that may be what we're looking for. This one may not go far enough. Yeah, 0.81 is over here, but our third standard deviation ends there. So this is the one we want to choose. Are the conditions necessary to use a normal model met? Our company compiles data. The national college freshman to sophomore retention rate was 76%. This doesn't say anything about how the data was collected, so I can't really analyze the randomization condition. But 76% of 600 is going to be bigger than 10, and 24% of 600, 1 minus 76, 24% of 600 is going to be bigger than 10, so the 10% condition is met, or our success failure condition is met. The 10% of condition, 600 students is certainly less than 10% of all students. So those two conditions are met, but I'm going to be concerned about that randomization because it's not really specified in the problem. Again, if these are typical of the students, but that's not really specified how they got it. So we've got to just say the randomization is an issue here because it wasn't specified. All right, so same thing, 74%. A certain college has 499 of the 595 freshmen return as sophomore. Does this college have an unusually high retention rate? Okay, so here's what we're saying. If I have a curve that's centered at 0.74, and we got 499 out of 595, which is 0.839. What's the probability of getting that or higher, right? We want to know, is that an unusually high retention rate? So I want to know, is that more than 2 standard deviations away from the 0.74? All right, so square root of 0.74 times 1 minus 0.74 over 595 is our number of freshmen. All right, we get 0.0179. So let's add that to the 0.74. Twice. So I should do times 2 plus the mean 0.74. And that's 2 standard deviations up. That would be 0.77. Well, this 0.83 is way beyond 0.77. So yes, this is more than 2 standard deviations up. Let's add one more and see if it's more than 3 standard deviations up. Yep, it's bigger than 3 standard deviations up. So yes, that's an unusual result. Now, why not go with 5 standard deviations? Because remember, our 68, 95, 99.7 rule, if I go up 3 standard deviations, that's more than 99.7% of my colleges. That's unusual. Did we do something wrong there on the, let's double check ourselves. And for 595, our mean was 0.74. Oh, I didn't read the sentence. It says is not more. All right, so it probably is over 5 standard deviations. So we can get that with the z-score. So the z, and by the way, I just didn't read the sentence. If this word not were there, then that would be a correct answer. So z equals, all right, our value was 0.839 minus 0.74, the mean. So this is our data value minus the mean over the standard deviation. We found that standard deviation to be 0.017, so 0.018. All right, let's figure out how many, what that z-score is. So if we go 0.839 minus 0.74 and divide by 0.018, that's more than 5 standard deviations up. So yep, it's more than 5 standard deviations. Just before a referendum on a school budget, a local newspaper polls 383 voters to predict whether the budget will pass. Suppose the budget has the support of 53% of the voters. What's the probability that the newspaper sample will lead it to predict defeat? Okay, so we've got 300. So here my N is the 383 voters. It has the support of 53, so then P is 0.53. So I'm centered at the 0.53, the actual value for the vote. But I want to predict defeat. That means that I would get less than 0.5%, less than 50%. So I want to find that area. Okay. So to find that area under the curve, we're going to use the normal CDF key. So, whoops. Second distribution, normal CDF. My lower bound is going to go to negative infinity, so negative 99999. Upper is the 0.5 is where the shaded area is stopping. Oops, sorry. When my mean is 0.53 and my standard deviation, I didn't calculate that. So let's see if it'll take the formula. Square root of 0.53 times 1 minus 0.53 is 0.47 divided by 383. Hopefully it'll take that formula. And we get 0.119. So to 3 decimal places would be 0.120. A sample is chosen randomly from a population that can be described by a normal model. Complete parts A and B below. What is the sampling distribution model for the sample mean? All right, so our sample mean would have a normal distribution with a center where our mean center is, and a standard deviation of the standard deviation divided by the square root n. If a larger sample is chosen, what is the effect of the sampling distribution model? The center will stay. The center will remain the same. There we go. But because the sampling size is bigger, that's gonna cause the standard deviation. This will be a bigger number down here, and I'm dividing by a bigger number. So the standard deviation will get smaller. A college's data about the incoming freshmen indicates that the mean of their high school GPA was 3.4 and a standard deviation of 0.2. The distribution was roughly mound-shaped and only slightly skewed. The students are randomly assigned to freshman writing seminars in groups of 25. What might the mean GPA of one of these seminar groups be? It would be the same, 3.4. And our standard deviation would be 3.4 divided by the square root of 25. Where did I say 3.4? Sorry, 0.2. The standard deviation divided by the square root of 25. So 0.20, so that would be 0.04. Oh, I didn't read this until just now. I didn't see that this was choice. Okay, so because I'm looking at skewed data, it says, oh no, it says it's only slightly skewed. So it's only slightly skewed, so it should still follow a normal distribution because that 25 is close to 30. That's a tricky question. In general, we require more than 30, but that's really when we've got, you know, anything that is coming from a normal distribution will continue to follow a normal distribution when the sample size is less than 30. So it's the fact that it's only slightly skewed that's allowing us to continue to say that. If it were badly skewed, then we'd pick B, that it's not normal because we're not getting over that sample size of 30. What assumptions and conditions must be satisfied for the sampling distribution model to be appropriate? The GPAs have to be independent. The students represent less than 10% of all possible students. And it's roughly unimodal and symmetric, so the sample is large enough. Make a sketch. All right, we're centered at 3.4, so we can rule out right here. Our standard deviation was 0.04. So 3.44, 3.48, and 3.52. So A. All right, assume that the duration of human pregnancies can be described by a normal model with a mean of 264 days and a standard deviation of 16 days. What percentage of pregnancies should last between 266 and 275? All right, so here's what we're doing. If I've got a normal distribution centered at 264, and a standard deviation is 16. So add 16 to that and we get to 280. Add 16 again. Add 16 again. Subtract 16. Subtract 16 again. Subtract 16 again. All right, that's what our sampling distribution looks like. Now we want to know what percentage is between 266 and 275 days. So I want that little bit of area right in there. Okay, so we're going to go to our calculator. We're going to go second distribution, normal CDF. The lower bound is the 266. The upper bound is the 275. The mean is the 264. And our standard deviation was 16. And we get about 0.204. Oh, so they changed it to a percent. So that's 20.44%. The longest 15% of all pregnancies would be some number, who knows what it is or where it is, but this area here would be 0.15. So for that, we use the inverse norm key, right? When we're given the area, we use the inverse norm key. So option 3, plug in that area, 0.15. When the mean is 264 and the standard deviation is 16. And I want to choose the right tail since this is on the right that I've shaded. And that'd be about 280. Oh, it said round to 1 decimal. 0.6. A normal model with, select the correct choice below and if necessary, fill in the answer boxes. All right, so this is a normal model with a mean oh, I see, C. Suppose a certain obstetrician is currently providing prenatal care to 67 pregnant women. Let Y bar represent the mean length of their pregnancies according to the central limit theorem. What's the distribution of this sample mean? So it would be a normal model with a mean at this 264 days and a standard deviation of 16 divided by the square root of 67. So let's figure that out. 16 divided by square root of 67, I think, was 1.95. The probability that the mean duration, oh, okay, will be at less than 257 days. So now we're using this mean and this standard deviation. 257 is here. So I'm shading this way, but not on this normal model that I've drawn, on the one that has this mean and this standard deviation. So let's go to our calculator. Second distribution, normal CDF. We want the lower bound to be infinity, so that's fine. Our upper bound, 257. When the mean is 264. And our standard deviation is 1.95. Point 0.000166. So we run to 0.0002. It is assumed that the duration of human pregnancies can be described by a normal model with a mean of 266 days and a standard deviation of 16 days. The results shown in the accompanying analysis of pregnancies were based on the normal model. The duration may not actually follow the normal model, however. Explain why the distribution may be somewhat skewed to the left. Okay, this doesn't relate to this, I don't think. There are more very long pregnancies than premature births, and there are very few pregnancies near the mean. There are more premature births than very long pregnancies, and there are very few pregnancies that are near the mean. There are more premature births than very long pregnancies, and nearly all pregnancies end by 2 weeks after the normal due date. There are more very long pregnancies than premature births, and it is rare for a birth to be more than 2 weeks premature. Well, if it's skewed to the left, then that would mean that we would have a few We'd have more very long pregnancies than premature births. And it would be rare for a birth to be more than 2 weeks premature. That would make sense with the skewness idea. If I'm skewed to the left, right, then we've got a tail to the left and a big hump. So over here where there's a short period of time, we should only have a few items. So a few premature births and not many that are more than 2 weeks would make sense with that. So I think our answer here should be D. Oh. I guess I didn't think through that very well, because if we have values over here, that means we don't have very long values over here. I wasn't thinking about that. So there would be more premature births than very long pregnancies. Okay, so that makes sense. And nearly all pregnancies end by 2 weeks after the normal due date. Yeah, I guess that's the case, right? Okay. That one took a little bit more thinking on my part. I apologize. All right. If the correct model is in fact skewed, does it change the results shown in the accompanying analysis that assumed that the normal model was true? No, because the normal model can still be used according to the central limit theorem, even though the correct model is very skewed because of our sample size being larger than, right? It's 60, that's larger than 30. So we're good, we should be good there. Our sample size, it said in there our sample size was 60. What did the question say? It said, oh, I didn't read the first 2 parts, I guess. When we look at this part wouldn't be true in this part. I was focused on the 60 women. This is not with the 60 women. So it's not fair to assume the normal model holds true if it's skewed. So yes, our results would change because the normal model cannot be used if the correct model is very skewed. Now, but the third part though, where we're using the sample of 60, that is okay because we're using a mean of a group and that will follow a normal model according to the central limit. Does the result in statement 2 change? I got to read a little careful. This was asking about statement 1, statement 2. So yeah, both statement 1 and statement 2 will change. There we go, D. But statement 3 is fine because it is the central limit theorem. All right. Carbon monoxide emissions for a certain kind of car vary with a mean of 2.251 and a standard deviation of 0.7. The company has 80 of these cars in its fleet. We want the distribution of the mean. So 2.251 is our mean. And our standard deviation is the 0.7 divided by the square root of 80. Point 078. We want to find the probability that we're between 2.4 and 2.5. So second distribution, normal CDF, the low is 2.4, the high is 2.5, the mean is 2.251, and our standard deviation is 0.078. Point 0273. All right, we want the probability the mean is bigger than something is 0.01. All right, so let's go second distribution, and now we're using the inverse norm. The area is the 0.1 we want to get back. The mean is the 2.251. And that standard deviation is the 0.078. And we're bigger than some value, so that's to the right. Why is that to the right? Let me show you. I guess I should be drawing this. So my mean's at 2.251. If the mean is bigger than something, this area is the 0.1. And that's what that second problem saying. 2.35. So 2.4. Weider believes the distribution of tips has a model that is slightly skewed to the right with a mean of 9.6 and a standard deviation of 5.4. Explain why I cannot determine the probability that a given party will tip him at least $20 because that's not normal if it's skewed. So I can't do probabilities on something that's not normal. Can you estimate the probability that the next 4 parties will tip an average of at least 15? No, because if it's skewed data, 4 is not big enough. It's not big enough for the central limit theorem, right? We got to be close to 30 for that. Is it likely that his 10 parties today will tip an average of 15? All right, it may not be large enough to use the normal model, but it's starting to approach it. So we could say the mean would be 9.6 and the standard deviation would be 5.4 divided by the square root of 10. So we wanted the probability. Oh, that his 10 parties today will tip an average of at least $15. So let's see how many standard deviations up that would be. 5.4 divided by the square root of 10. Is 1.708. So if our mean is 9.6 plus 3 times those standard deviations would not approach $15. So no, it's not likely. Okay, so A sounds pretty good to me. That seems to capture everything we said right there. As the sample size increases, the mean of the sampling distribution will stay exactly the same. As the sample size increases, the standard deviation of the sampling distribution is given by the standard deviation divided by the square root of sample size. So this is increasing, this gets smaller. All right, guys, that is the chapter 17. I'm going to let that be it for now so that we can stop this recording and I can post it. And I'll come back and I'll do chapter 11. We'll do that in the morning.